Okay, so this will be the prep video for section 5.1. We're going to introduce a new concept kind of entirely. It's called antiderivative or indefinite integral. So far we've been doing everything about doing derivatives, and so we know some things. Let's review. We know that if we have a power function, x to the n, we know that if we differentiate with respect to x, that we will get a derivative, and its derivative is nx to the minus 1. Okay, so we've been doing that a bunch. So let's write out the other ones we know. We know e to the x, the derivative is e to the x. We know ln x, the derivative is 1 over x. So going in this direction, we're differentiating. You might guess correctly that going in this direction, we'll be doing anti-differentiation. So when I do the derivative, I know my rules, but I can start with the derivative and work my way backwards to the original function. So notation that we're going to use is we're going to call capital F the antiderivative of the function. So that means that when I go in this direction, if I take the derivative of f prime, I'll get the function. If I start with the function and do the antiderivative, I get to the antiderivative. So the thing to remember here is finding the derivative of the antiderivative. Those operations undo each other. So the derivative of the antiderivative just gets back to the original function, the original thing you started with. Okay, so let's do some examples. If we start with, I guess, I'm going to keep adding it down here. If I start with f of x equals 3x squared, what will the antiderivative be? That means what is a function whose derivative is 3x squared? Well, we know if we start with x cubed, from the power rule, the derivative would be 3x squared. So that means the antiderivative is x cubed. Okay, that makes sense. And we can check that by doing the derivative, and we get back to the right place. Let me ask you this. Is this also an antiderivative? Well, let's check. Remember, we do the derivative to check. So if I do the derivative of x cubed plus 5, I'll get 3x squared plus 0. So both of these have a derivative of 3x squared, which means either one of them can be an antiderivative. In fact, what about this one? Sure. In fact, it doesn't matter what I add, because when I go back and do the derivative step to go back to check, the derivative of these constants, no matter what the constant is going to be 0. So all of these are possible antiderivatives for that. So as a result, we use a more general form, and we will say, we would write it this way. The antiderivative of 3x squared is x cubed, because that gives me this as a derivative, plus c, because it could be really any constant. And later we will have more information where we can find this plus c, but for now we don't. And so we call this, right here with the plus c, the general solution. So let me come over here and list a bunch of vocabulary. Today will be a lot of vocabulary, a lot of introduction of new terms that all pertain to this anti-differentiation process. Okay, so a differential equation is where you know something about the derivative. So you might know this. F prime is some function. You know the derivative, and you want to find the antiderivative. So we call that the general solution. The general solution would be f of x plus c. And it's general because we're not specific, right? We don't know what c is. We'll find that later, for some cases and not for others. Okay, so that's the general solution. The process of doing that is called anti-differentiation. Or alternatively, indefinite integration. And I'll introduce that in just a sec. What else do we know? This plus c has a name as well. We call that the constant of integration. And what else? Oh, and then lastly, we're going to introduce it. So this idea of doing anti-differentiation, just like with derivatives, we have ddx, which says do the derivative with respect to x. This is like a verb, an instruction. We have a similar thing for integration, and it's this shape. It looks kind of like an S, but really tall and skinny. And that is called an integral sign. And it's an action, it's a verb. This tells you what to do. This says do the integration. So anti-differentiate. Now, just like with derivatives, you need to know with respect to what. The same thing is true for integrals. And so, finally, as kind of a final form, we will have equations that look like this. So let's look at these parts. Y equals, you don't have to have that part, but sometimes we'll use that. This says, do find the antiderivative, or do the antidifferentiation with respect to x. This is really important. You have to have that piece always, because partly it's part of the instruction. You need to know which variable to do the antidifferentiation with respect to. And then this, remember, we've said that capital F is the antiderivative of little f. We have to add the plus c because really any number of constants, an infinite number of constants would work. And so since we don't know that information, we just call that plus c. So what else do we need to have? So when you have a problem, then how will you know that you need to do an antiderivative? Well, anytime you see this integral, and we call this the integral, anytime we see the integral of a function, that's automatically an instruction that says to antidifferentiate. Another thing you might see, though, is you might see find the general antiderivative of f of x. So do the integral, find the general antiderivative. It might say find, it might actually say in words, find the indefinite integral. That would be essentially, if you were given this, the words for that would be find the indefinite integral. And lastly, it might say, here's the derivative, find the original function. So given the derivative, find the original function. So in other words, all of these are saying find the antiderivative. Just different ways of saying it. Okay, so let's do some examples. Okay, so here's one. The instructions are find the general antiderivative for the following functions. Find the general antiderivative. Okay, so here's the first one. F of x equals 2x. So the question is, what is a function whose derivative is 2x? Well, so let's think about that. Does 2x look like a familiar derivative? It does. It would be the derivative for x squared, right? Derivative of x squared is 2x. I recognize that as a common derivative I have seen. I have to add the plus c because, again, any number of constants would work. What about this one? Actually, I'm going to leave some space here for a sec. What about this one? 3x squared. Does that seem like a familiar derivative? It does. We know that x cubed, the derivative, is 3x squared. And again, plus c, because the derivative of the plus c would be 0. So any constant at all will work. Okay, so here are cases where we have recognized these as direct derivatives of these. So what happens if instead I just have x Well, that's not a full antiderivative of anything. If you like to, you can think of it this way. It's kind of like 1/2 times 2x. I've just multiplied by 2 over 2, so I haven't changed anything. This I recognize. I know that this is a derivative of x squared. What do I know about multiplication? Multiplication by a constant carries through. That's true when we're doing derivatives this way. This way is also true when we're doing antiderivatives. So this one, the antiderivative, will be the 1/2 times, I recognize this as the derivative of x squared plus c. So I don't have to have the full antiderivative in order to do this. We're going to develop a rule for this for power functions, but let me just kind of remind you about what we're doing, and then we'll develop a general rule. So here's another one. What if I just have x squared? Well, again, x squared is not a full derivative of anything, but I could write this as 1/3 times 3x squared. This one is the full antiderivative of x cubed, and then I have this 1/3 carries through. Okay, so we're starting to see a pattern if we start to look at this. The derivative of x is x squared divided by 2. The derivative of x squared, try this again, the antiderivative of x is x squared divided by 2. The antiderivative of x squared is x cubed divided by 3. So it might be reasonable to expect that the antiderivative of x cubed would be raise the power x to the 4th, divide by. And that would be true. So you can work this out in the same way and verify that that's true. So now let's take a look and kind of write some. So we have our language here, our new vocabulary. Let's write a short list of rules, and then we'll do some more antiderivatives. So here are basic, this is our vocabulary, and let's put here our basic integration rules. And hopefully I'll have a little space in the middle to work some problems. So we know that the integral of x to the n dx, this is the power rule we were just developing. This will be x to the n plus 1. Remember, it's going to go in the opposite direction of derivatives. Derivatives, you decrease the power by 1. Antiderivatives, you're going to increase the power by 1. Derivatives, we multiplied by n. Integrals, we're going to divide by the power. Okay, we have this one. Integral of e to the x. We love e to the x because when we take derivatives, it's itself. So naturally, when we take antiderivatives, it's also itself. And then lastly, derivative of 1 over x. What is 1 over x the derivative of? It's the derivative of ln x. So its antiderivative is ln x. But now we have to be a little bit careful. We need to remember that logs have a domain issue. You cannot take the log of a negative number. And here, it's not clear whether they're negative numbers or not. So we need absolute values around that. And then what else do we know? Multiplication by a constant carries through, as does addition and subtraction. So these all carry through. Okay, so one thing that's missing here is there's not a reverse power of a reverse product rule, nor is there a reverse quotient rule. They don't exist. And we will have a reverse chain rule. We'll get to that next time. But the antiderivatives that we're going to cover in this class are really going to fall in this category plus chain rule. Okay, so let's do some examples. Let's find, see if I can carve out some space. Find the indefinite integrals for f of x equals 4x cubed. Let's start with that one. Okay, we know that if we recognize this, you may recognize this as the full derivative of x to the fourth, so the antiderivative will be x to the fourth. Let's use this new power rule though, just to practice with it. So this says, take the power and raise it by 1, so that's x to the third becomes x to the fourth, and then divide by 4. So 4 divided by 4 is 1, so I don't need to write it, and then plus c. All right, let's try this one. F of x equals 3x to the fourth. We need to be careful because these kind of look similar, and so it's easy to mix them up perhaps. Again, let's apply the power rule. So we're going to take this exponent and raise it by 1, x to the fifth, and then divide by that number. So 3 divided by 5. And the reason we keep the 3 is because multiplication carries through. We know that. All right? So that's one set. Let's do another one. Find the general antiderivative So again, what does that say? Both of these, find a definite integral or general antiderivative, both mean to do the antidifferentiation with the plus c. That's the indefinite and the general part. We're going to get to specific solutions and definite integrals. Those will not have a plus c, and we'll talk about those later. All right, so here's one. dy dt equals 15 e to the t. So this is a different way of writing it, but this says I know the derivative, find the general antiderivative. Okay, so the antiderivative of dy dt will be y. The antiderivative of e to the t is e to the t. Multiplication by a constant, 15, carries through. General means I have a plus c. All right, what about this one? dp dt is 15 divided by t. Again, I know the derivative. I want to find the antiderivative. So the antiderivative of dp dt is p. The antiderivative, so this one, we may want to break this apart and write 15 times 1 over t. Sometimes that makes it a little bit easier to see. Because if I tried to write this as a power rule, if I tried to write this 15 t to the minus 1, it's common to think that would be reasonable, right? That's what we do when we're doing derivatives. We pull things out of the denominator to put them into power rule form. So if you do this here, then what happens? We raise the exponent, so we would get t to the 0, and then divide by that. Clearly that doesn't work. So anytime you do this, you're going to find the answer makes no sense. Okay, so that's fine. Why does the answer make no sense? It makes no sense because it's not a power. 1 over t, this is a ln, right? Come back over here. The integral of 1 over x dx is ln x. So this, one more space, this is going to be ln t. General means plus c. Multiplication carries through. So 15 ln t. Okay, one last one. N prime of x equals 1 over 3x squared. Big difference between these two? 1 over a variable to the first power is a ln. 1 over a variable to anything except that is a power. So this one I do need to rewrite. So let's rewrite that as x to the minus 2. The 1/3 stays, right? The 3 is not, when I change the x squared, that's not affecting the 3. So that 3 stays in the denominator. Okay, so this is set up for power rules. So let's remember what we do. We raise the power by 1 and then divide by that number. So n of x, raise the power by 1, divide by negative 1. So 1/3 divided by negative 1 is just negative 1/3 plus c. So multiplication carries through, plus c is your general antiderivative. Okay? Just a few more. Let's see if I can. I know it's a little bit crowded. I'm just trying to keep up all the general terms and information in case you need to refer to them while we're doing the problems. Okay, so here is one last one. So I present to you this, 2x to the 5 halves minus square root of x plus 1 dx. So remember, what does this tell you? This is an integral sign that is a verb. It's an action, it's a direction. This says to find the antiderivative of this. So let's look through here and see. This looks like a power rule. No problem. It's fractions in the power, but that's okay. This one, just like with derivatives, we can write this in a power rule form, so we need to go ahead and do that. And then 1, we haven't talked about 1 yet. We'll talk about that. Okay, so let's rewrite. The parentheses are important because you're saying that this instruction, find the antiderivative, applies to the entire thing with respect to x. So we'll have 2x to the 5 halves minus x to the 1 half plus 1 dx. Okay, what do we know? Addition carried and subtraction carried through. So that means I can do these one at a time, doing the antiderivative. This is a power rule. So I'm going to take the exponent, raise it by 1. 5 halves plus 1 is 7 halves. And then divide by it. Or, rather than dividing by a fraction, we know when we divide by a fraction, we multiply by the reciprocal. So we can just do that straight away. So we have 2 times 2, because multiplication carries through, 2 times the reciprocal of that, 2/7. Okay, what about this one? X to the 1 half becomes x to the 3 halves. Divide by 3 halves, multiply by the reciprocal. And now, what do we think about 1? What is the antiderivative of 1? Well, I could write it as 1 x to the 0. And so if that's a power. So if I raise the power by 1 and divide by, I just get x. Does that make sense? Sure, we recognize 1 as the full derivative of x, which means the antiderivative of 1 is x. So we just have x, and then we have each of the terms plus c, because this is an indefinite integral. We'll see later when we get to definite integrals, there'll be more information, but this automatically, the way it's written, tells you indefinite. Now we just need to clean it up, so 4/7 x to the 7 halves minus 2/3 x to the 3 halves plus x plus c. Okay, so that is the basic part for this new material. It's not hard, but it is a kind of a reverse way of thinking. So I encourage you, please, to do the prep assignment to make sure that you're ready to go for class. So again, we're talking about doing the reverse of taking the derivative. We're going backwards. So our rules go backwards, and you can always check by doing the derivative. The derivative of the antiderivative should get you back to the function. So if you're not sure if you've done the antiderivative correctly, do the derivative and check. In fact, I think some of the problems had that as part of the instructions, so pay attention to that. Okay, that's it.